April 19, 1945. East China Sea, 12:23 hours. The 16-inch shell left the barrel of USS Iowa's forward turret at 2,700 feet per second, a 1-ton projectile of hardened steel, and high explosives accelerating through salt air with enough kinetic energy to level a city block. The sound arrived after the shell had already traveled hundreds of yards of thunder crack that rolled across the water and rattled the fillings in the teeth of sailors standing on deck. In the turret, men moved in practice choreography despite ringing ears and noses bleeding from overpressure. Powder bags had been rammed. The breech had been closed. The firing pin had struck. And now, somewhere beyond the horizon, a Japanese destroyer was about to learn what American industrial might look like when compressed into a single, terrible instant of impact. The shell was not just a weapon. It was a culmination of metallurgy, chemistry, precision engineering, and industrial capacity operating at scales that defied comprehension. Each projectile represented hundreds of man-hours, tons of raw materials, and the coordinated effort of factories, railroads, and shipyards spanning the continent. To understand this shell was to understand how America fought the Second World War, not through superior tactics or individual heroism alone, but through the methodical application of overwhelming material advantage. The shell was abundance, made, lethal. It was democracy's answer to tyranny, forged in steel and delivered at supersonic speeds. But before the shell could tear through armor plate and detonate inside an enemy vessel, it had to be made. And the making of a 16-inch armor-piercing shell was an engineering challenge that pushed the limits of 1940s industrial technology. It began not in a factory, but in a mine, where iron ore was extracted from the earth in quantities measured not in pounds, but in millions of tons. The ore traveled by rail to blast furnaces, where it was smelted into pig iron, then refined into steel alloys capable of withstanding pressures and temperatures that would destroy ordinary metal. The steel was cast, forged, heat-treated, machined, filled with explosives, and finally fitted with precision fuses that determined whether the shell would detonate on contact or after penetrating deep into an enemy ship's vitals. Every step required expertise, precision, and resources. Every step was a testament to industrial capacity. By 1945, the United States had been mass-producing naval shells for 3 years, and the scale of production was staggering. American factories turned out tens of thousands of large-caliber projectiles every month, feeding an appetite for firepower that seemed insatiable. The battleships and cruisers of the U.S. Navy consumed ammunition at rates that would have bankrupted any other nation. A single broadside from a battleship's main battery could expend shells worth more than the average American worker earned in a lifetime. Yet the shells kept coming, an endless stream of ordnance flowing from factories to depots to ships, each one representing a fragment of America's industrial dominance. The Japanese, who faced this deluge of firepower, had entered the war confident in their own technological prowess. Japanese naval shells were excellent, perhaps the best in the world in terms of explosive content and armor penetration. Japanese metallurgists had developed steel alloys and manufacturing techniques that produced projectiles of exceptional quality. But quality, they discovered delayed, could not compensate for quantity. American shells were good enough, and there were so many of them that good enough became overwhelming. For every Japanese shell fired, American ships answered with 10, 20, 50 in return. The mathematical inevitability of industrial warfare asserted itself with brutal clarity. The side that could produce more, faster, and longer would win. But the shell itself, the physical object that represented this industrial advantage, was far more complex than its simple appearance suggested. To the untrained eye, a 16-inch shell looked like an oversized bullet, a pointed nose, a cylindrical body, a flat base, but every dimension, every curve, every material choice was the result of careful calculation. The shell had to be aerodynamic enough to maintain accuracy over distances exceeding 20 miles. It had to be strong enough to survive the immense acceleration of being fired from a gun barrel, a process that subjected it to forces equivalent to being dropped from a building onto concrete. It had to be hard enough to punch through armor, plate thicker than a man's torso, yet not so brittle that it shattered on impact. And it had to carry enough explosive to destroy whatever it hit after penetrating the target. The construction of a 16-inch armor-piercing shell began with the projectile body, a massive cylinder of forged steel weighing roughly 2,700 pounds. Before Final machining and filling. The steel was not ordinary, it was a carefully formulated alloy, typically containing chromium, nickel, and molybdenum in precise ratios that gave it the necessary combination of hardness and toughness. Too hard, and the shell would shatter on impact. Too soft, and it would deform without penetrating. The metallurgists who developed these alloys worked with tolerances measured in fractions of a %, testing sample after sample until they found a combination that could survive the twin ordeals of launch and impact. The forging process itself was a spectacle of controlled violence. A steel ingot, heated to glowing orange, was placed under a massive hydraulic press that applied thousands of tons of pressure, compressing the metal grain structure into dense, uniform consistency. The ingot was rotated and pressed repeatedly, each blow forcing impurities to the surface where they could be removed. The result was a solid steel billet with mechanical properties far superior to cast metal. This billet was then machined on lathes capable of handling workpieces weighing over a ton, cutting away excess material until the projectile assumed its final shape. Heat treatment followed. The shell body was heated to precise temperatures, typically around 1,500 degrees Fahrenheit, and then quenched in oil or water, a process that hardened the steel by transforming its crystalline structure, but hardening alone created brittleness. So the shell was tempered, reheated to a lower temperature, and slowly cooled, a process that relieved internal stresses and gave the metal the toughness it needed to survive impact. Getting the heat treatment right required skill and experience. Too much hardening created shells that shattered. Too much tempering created shells that bent without penetrating. The window for success was narrow, and quality control inspectors rejected any shell that fell outside specifications. With the shell body forged and heat treated, attention turned to the explosive filler. American armor-piercing shells typically used a relatively insensitive explosive called explosive D, a picric acid-based compound that was stable enough to survive the shock of being fired from a gun and penetrating armor, yet powerful enough to destroy a ship's interior when detonated. The explosive was melted and poured into the shell's hollow cavity, a cylindrical void, running through most of the projectile's length. As the explosive cooled and solidified, it formed a solid mass weighing several hundred pounds, transforming the shell from a solid projectile into a bomb. But the explosive was useless without a fuse, and the fuse design was where much of the shell's sophistication resided. An armor-piercing shell could not detonate on contact with the target's outer hull. That would waste the explosion against armor plate designed to absorb such blasts. Instead, the fuse had to delay detonation until the shell had penetrated deep into the target, ideally reaching magazines, engine rooms, or other critical spaces before exploding. This required a fuse that could distinguish between the initial impact with armor and the subsequent penetration into the ship's interior. American designers developed several fuse types, but the most common for armor-piercing shells was the base detonating fuse with a delay mechanism. This fuse was installed in the base of the shell, protected from the initial impact by the shell's own momentum. When the shell struck armor, the sudden deceleration armed the fuse. As the shell punched through and entered the ship's interior, a small delay element, typically a powder train, that burned at a precise rate, counted down the fractions of a second before triggering the main explosive charge. If everything worked as designed, the shell would penetrate deep into the target before exploding, maximizing damage to vital systems. The precision required to manufacture these fuses was extraordinary. The delay mechanism had to be reliable across a wide range of impact angles and velocities. Too short a delay, and the shell would explode while still in the armor, wasting much of its destructive power. The longer delay, and the shell might pass completely through the target before detonating, exiting the far side and exploding harmlessly in the water. Fuse manufacturers tested their products rigorously, firing shells at armor plate under controlled conditions, and measuring the time from impact to detonation with high-speed cameras and instrumentation. Batches that failed to meet specifications were scrapped, a costly but necessary measure to ensure that shells fired in combat would perform as expected. The final component was the windscreen or ballistic cap, a pointed nose cone fitted over the blunt front of the shell to improve aerodynamics. Without this cap, air resistance would rob the shell of velocity and accuracy over long ranges. The windscreen was designed to shatter on impact, absorbing some of the initial shock and helping to align the shell's trajectory perpendicular to the armor plate. Behind the windscreen, Many armor-piercing shells included a hardened cap-thick steel nose designed to prevent the shell's tip from shattering on impact. This layered structure windscreen, hardened cap, main body gave the shell its distinctive appearance and ensured that each component failed in sequence, absorbing energy while protecting the integrity of the projectile and its explosive payload. When all components were assembled, the finished shell weighed approximately 2,700 pounds for a 16-inch projectile. Though weights varied depending on shell type, armor-piercing shells were the heaviest, followed by high-capacity shells designed for short bombardment, and finally, special-purpose projectiles like illumination rounds. Each shell was marked with paint bands indicating its type and lot number, allowing crews to identify ammunition at a glance even in the chaos of combat. Quality control inspectors examined every shell, checking dimensions with precision instruments and performing non-destructive tests to detect internal flaws. Shells that passed inspection were transported to naval depots, where they were stored in climate-controlled magazines, protected from moisture and temperature extremes that could degrade explosive fillers or corrode metal components. The journey from factory to target was long and carefully choreographed. Shells traveled by rail from manufacturing plants to coastal depots, then by tender to fleet anchorages, where they were loaded aboard warships. Loading a battleship's magazines was a task that required days and hundreds of sailors working in coordinated teams. Each shell had to be hoisted from the tender's hold, transferred to the battleship, and lowered into magazines located deep in the ship's armored citadel. The shells were stacked in racks, secured against the ship's rolling and pitching, and inventoried meticulously. A battleship might carry over 1,000 rounds for its main battery alone, representing hundreds of tons of ordnance and millions of dollars in manufacturing costs. When the call to action came, the shells began their final journey from magazine to gun. In a battleship's turret, the process was mechanized but still required human hands at every stage. A shell hoist lifted projectiles from the magazine to the gun house, a rotating armored structure containing 3 massive guns arranged side by side. The shell arrived first, rolling on a cradle into position behind the gun's breech. Hydraulic rammer, arms powerful enough to dent steel if mishandled, shoved the shell into the barrel, a process that had to be smooth and precise to avoid damaging the projectile or scratching the barrel's rifling. Behind the shell came the propellant, silk bags filled with smokeless powder, each bag carefully weighed to ensure consistent muzzle velocity. The number of bags varied depending on the desired range. More powder meant higher velocity at longer range, but also more wear on the gun barrel. With the shell and powder loaded, the breech was closed, a massive steel plug that sealed the gun chamber and contained the explosion of burning propellant. The gun captain checked his firing solution, data computed by the ship's fire control systems and transmitted electrically to the turret. Elevation and bearing were adjusted using hydraulic drives that moved the gun smoothly despite their immense weight. When everything was ready, the order to fire was given. An electrical signal traveled from the fire control center to the turret, where it triggered the firing pin. The primer ignited, setting off the powder bags in a controlled explosion that generated pressures exceeding 40 pounds per square inch and temperatures hot enough to melt steel. In the microseconds it took for the powder to burn, those pressures accelerated the shell from 0 to over 2,700 feet per second, launching it out of the barrel with kinetic energy equivalent to a loaded truck hitting a wall at highway speeds. The physics of what happened next were elegant and brutal. As the shell left the barrel, rifling grooves cut into its rotating band of soft copper or brass ring fitted around the shells, base imparting a spin of several hundred revolutions per second. This spin stabilized the shell in flight, preventing it from tumbling and ensuring that it maintained its nose-forward orientation. The shell's flight path was a parabola, arcing high into the sky before descending toward the target. At longer ranges, shells could climb to altitudes exceeding 30,000 feet, spending over a minute in the air before impact. During this time, the shell was subject to gravity, air resistance, wind, the Coriolis effect from the Earth's rotation, and even variations in air density and temperature. Fire control computers, massive electromechanical devices that occupied entire rooms, calculated corrections for all these factors, adjusting gun elevation and bearing to ensure that shells landed where intended. When the shell finally struck its target, the impact was catastrophic. A 16-inch armor-piercing shell hitting at terminal velocity, typically around 1,600 to 2,000 feet, per second depending on range delivered energy measured in millions of foot-pounds. The shell's hardened nose punched through armor plate like a hammer through glass, creating a shower of spalling sharp fragments of armor blown inward by the impact. The shell itself, designed to remain intact during penetration, continued through bulkheads, decks, and machinery, carving a path of destruction until the fuse delay expired and the main explosive charge detonated. The explosion, contained within the ship's structure, generated pressures that buckled steel, ignited fuel and ammunition, and shattered everything within dozens of feet of the blast center. For Japanese sailors who experienced this firepower, the psychological impact was as devastating as the physical destruction. Japan had entered the war with confidence in its navy, particularly its battleships. Ships like Yamato and Musashi were the largest and most heavily armed battleships ever built, their 18-inch guns theoretically superior to anything the Americans could field. Japanese naval doctrine emphasized quality over quantity, believing that superior ships crewed by superior sailors would overcome any numerical disadvantage. This confidence was not irrational. Japanese warships were well designed, and Japanese sailors were highly trained. But doctrine written in peacetime could not account for the industrial realities of total war. The Americans did not need superior individual ships. They had enough good ships to overwhelm any opponent through sheer volume of fire. Japanese battleships, for all their might, could only be in one place at a time. American task forces operated with multiple battleships supported by cruisers, destroyers, and carriers, creating concentrations of firepower that no single enemy ship could survive. When American shells began landing on Japanese vessels, the effect was both physical and psychological. The volume of fire was unrelenting. Shells that missed simply created geysers of water that obscured vision and rattled crews. Shells that hit destroyed armor, killed sailors, and set fires that spread faster than damage control parties could contain them. Japanese ships, designed to give as good as they got, found themselves unable to respond effectively. Their shells were excellent, but there were a few of them. Their fire control was sophisticated, but it could not compensate for being outnumbered and outgunned. The symbolic power of the 16-inch shell extended beyond its tactical effectiveness. To American sailors, the shell represented their nation's industrial might, a tangible reminder that they fought not alone, but backed by factories, mines, and shipyards that could produce weapons faster than the enemy could destroy them. The sound of the guns firing was not just noise, it was reassurance. It said, "We have more. We can afford to fire as many shells as it takes. We will not run out." This psychological advantage was difficult to quantify, but impossible to dismiss. Sailors who knew they had ample ammunition and supplies fought with a confidence that those facing shortages could not match. For the Japanese, the shell became a symbol of overwhelming disadvantage. As the war progressed and American firepower only increased, Japanese sailors came to dread encounters with American surface forces. The math was simple and inescapable. Every engagement inflicted losses Japan could not replace. Every shell fired depleted magazines that could not be refilled. The industrial base that had seemed adequate in 1941 revealed itself as grossly insufficient by 1944. Japan could build excellent ships and produce excellent shells, but not in the quantities needed to match an enemy whose factories worked around the clock and whose resources seemed limitless. The 16-inch shell, repeated thousands of times, became the physical manifestation of industrial defeat. The shell's design also reflected broader American approaches to warfare, where Japanese engineering often prioritized elegance and optimization, squeezing maximum performance from limited resources. American engineering emphasized robustness and scalability. American shells were not the most sophisticated in the world, but they were good enough and could be produced in staggering numbers. This philosophy permeated every aspect of American military production. American tanks were mechanically simpler and less powerful than German Tigers, but there were vastly more of them and they were easier to repair. American aircraft were often outperformed by German or Japanese fighters in specific metrics, but American factories produced them by the tens of thousands, while enemy production struggled to keep pace with losses. The 16-inch shell was part of this pattern, a weapon designed not for individual perfection, but for mass production and overwhelming application. The manufacturing infrastructure that made this possible was itself a weapon. By 1943, the United States had mobilized its economy for total war to an extent that no other nation matched. Factories that had produced automobiles now produced tanks and aircraft. Chemical plants that had made fertilizer now made explosives. Steel mills ran at capacity, turning out plate, bar, and billet for ships, guns, and shells. Women entered the workforce in unprecedented numbers, taking jobs at factories and shipyards that had been exclusively male before the war. The mobilization was not without friction. Labor disputes, material shortages, and logistical challenges plagued production throughout the war, but the scale and speed of the transformation were nonetheless remarkable. In 1940, the U.S. military was ranked 19th in the world by size. By 1945, it was the most powerful military force in human history, equipped with weapons produced in quantities that seemed almost absurd. The shell's journey did not end with impact. After the war, naval architects and metallurgists studied the effects of shell fire on captured and sunken Japanese vessels, seeking to understand how their weapons had performed and how future designs might be improved. Examination of armor plate revealed the characteristic punch-through holes left by armor-piercing shells, surrounded by spalling and fractures that indicated the force of impact. Internal damage documented by salvage teams showed the devastating effects of shells that had detonated inside ships, blowing out bulkheads and collapsing decks. These studies informed post-war shell design, though by then the relevance of battleship-caliber guns was already declining. The advent of guided missiles and aircraft carriers armed with jet aircraft meant that the era of the big gun battleship was ending. The 16-inch shell, perfected through years of combat, would fire its last shots in anger decades later in different conflicts, but never again as the dominant weapon of naval warfare. Yet the shell's legacy persisted in less obvious ways. The metallurgy developed for armor-piercing projectiles found applications in civilian industry, where high-strength steels became essential for construction, tooling, and manufacturing. The precision machining techniques required to produce shells to tight tolerances translated into improved quality control in post-war manufacturing. The logistical systems developed to move millions of tons of ordnance from factory to front lines became the foundation of modern supply chain management. Even the fire control computers that aimed at guns primitive by modern standards, but cutting edge for their time, represented early steps toward the digital computing revolution that would transform the post-war world. For the sailors who fired these shells and the sailors who died under their impact, the 16-inch projectile was not an abstraction or a symbol. It was a physical reality that defined their experience of war. American gunners remembered the bone-shaking concussion of firing, the acrid smell of burned powder, the satisfaction of seeing a target disappear beneath a column of water and smoke. They remember the weight of shells during loading drills, the heat of turrets after prolonged firing, the exhaustion of combat that left ears ringing and muscles trembling. These memories, shared among veterans in the decades after the war, formed a collective understanding of what it meant to serve aboard ships that could project such devastating firepower. Japanese survivors remember the terror of being on the receiving end. They remember the sound of shells incoming, a shrieking whistle that gave only seconds of warning before impact. They remember the shock waves that knocked men off their feet, the flash and roar of explosions, the screams of wounded comrades, and the smell of burning oil and flesh. They remembered helplessness, the knowledge that there was no defense against shells, arriving faster than sound, no way to shoot them down or evade them, nothing to do but endure and hope the next one would miss. For many, the most haunting memory was not the shells that hit, but the ones that didn't, the near misses that created massive waterspouts that drenched the ship and reminded them how thin the line was between survival and annihilation. The 16-inch shell, in all its brutal simplicity, embodied a truth about modern industrial warfare, that victory belonged not to the bravest or most skilled, but to those who could produce and deliver the most firepower for the longest time. Courage and skill mattered. Individual acts of heroism and tactical brilliance could win battles, but wars were won by factories, railroads, and the ability to turn raw materials into weapons at scales that overwhelmed the enemy's capacity to resist. The shell was a physical manifestation of this reality. Each one represented tons of steel, pounds of explosives, hours of skilled labor, and the coordinated effort of an industrial system that spanned a continent, multiplied by thousands, then tens of thousands, then hundreds of thousands. The shells became not just weapons, but a statement. America could afford to fight this way, and its enemies could not. This was the lesson that Japan learned late. In the years before Pearl Harbor, Japanese planners had calculated that American industrial capacity would eventually prove decisive. If the war dragged on, their strategy had been to strike hard and fast, achieving victories that would demoralize the Americans and force a negotiated peace before industrial production could be fully mobilized. But the strategy failed. American morale did not break. The industrial mobilization happened faster than Japanese planners had thought possible. And once American factories hit their stride, the output was overwhelming. By 1944, the disparity in production had become so vast that Japanese forces were fighting not a war, but a delay in action, trading lives for time in battles whose outcomes were predetermined by material imbalance. The shell also revealed the moral ambiguities of industrial warfare. Each 16-inch projectile cost thousands of dollars and required enormous resources to produce, yet it was fired and forgotten in seconds. The economic inefficiency was staggering. A weapon that represented weeks of labor and tons of materials was used once and destroyed, either by impact or by missing its target and sinking into the ocean. Yet this profligacy was also the source of American strength. Only a nation with vast resources and industrial capacity could afford to fight this way. Treating expensive munitions as expendable, the wastefulness that appalled observers from less wealthy nations was, paradoxically, a form of efficiency. It was cheaper to overproduce and accept waste than to ration ammunition and risk losing battles for lack of firepower. This approach to warfare, prioritizing overwhelming force over economy, had profound implications. It meant that American strategy could be direct and straightforward, relying on superior firepower to compensate for any tactical disadvantage. It meant that American commanders could be aggressive, knowing that losses of equipment could be replaced quickly. It meant that American sailors and soldiers fought with a psychological advantage, confident that they had the best and most plentiful weapons. But it also meant that the American way of war was inherently unsustainable for any nation that lacked comparable resources. The tactics and strategies that worked for the United States could not be replicated by allies or enemies with smaller industrial bases. American military doctrine was, in a sense, a luxury good available only to the world's wealthiest nation. In the final year of the war, American battleships ranged close to the Japanese home islands, using their 16-inch guns to bombard coastal installations and industrial targets. The shells that had been designed to pierce battleship armor were now falling on factories, rail yards, and military bases, their massive explosive charges obliterating structures and equipment. These bombardments were less tactically significant than the strategic bombing campaign carried out by B-29s, but they were symbolically important. They demonstrated that American forces could approach Japan with impunity, standing off the coast and methodically destroying targets, while Japanese defenders could do little to stop them. The guns that had been built to fight enemy battleships found their final targets not at sea, but on land, reducing the infrastructure that sustained Japan's war effort to rubble and ash. For the veterans who lived through the era of the big gun battleship, the shell remained a powerful memory in reunions and oral histories. They spoke of the awesome power of the 16-inch guns, the way the deck shook when they fired, the way the shells traced arcs of destruction across miles of ocean. They spoke with pride of the weapons they had wielded and with respect for the engineering and labor that had made those weapons possible. And they spoke with somber recognition of what those weapons had done. The ship sunk, the lives ended, the destruction wrought. The shell was both achievement and tragedy, a symbol of human ingenuity turned toward purposes that saved some lives by ending others. In the end, the 16-inch armor-piercing shell was more than a weapon. It was a crystallization of industrial modernity, a product of systems so complex and resources so vast that no single person could comprehend the totality of its creation. From the iron ore torn from the earth to the shell's final impact on a distant target, every step involved the coordinated effort of thousands of people working in mines, factories, railroads, shipyards, and warships. The shell was proof that modern war was not decided by individual warriors, but by entire societies mobilized for production. It was a monument to human capability and a warning of human destructiveness. It represented the apex of an era when battleships ruled the seas, and big guns defined naval power, an era that would end with the war that had pushed their development to its ultimate expression. And as the shell arched through the sky on that April day in 1945, carrying with it the concentrated effort of a nation at war, it traced a parabola that connected factory to target, worker to sailor, production to destruction. It was a messenger, announcing in the language of fire and steel that the age of American industrial dominance had arrived, and that those who faced it would be broken not by any lack of courage or skill, but by the simple, brutal mathematics of overwhelming force. The shell spoke, and the message was clear. This was how America fought. This was how America won, and against this tide of iron and explosives, delivered without pause and without mercy, no enemy could stand forever.